Hello everyone, this is Jemin from Retro. In this video series, we will dive into shader programming in Unity and explore how rendering works in game engine and graphics. Even though we're gonna talk about Unity, the principle we cover are also applicable for understanding rendering shader in other game engines like Unreal Engine. The first few videos, we're gonna talk about how rendering and shader works. And then we're gonna write shader code in Unity project. Today's episode will introduce what shaders are and why they're used in simple and abstract sense. Shader can be defined in two ways. If we define shader by their purpose, we can say shader are programs that print colors on your screen. That's why they're called shader. Secondly, by how they operate. Within the graphics rendering pipeline, shaders are the programmable components that you can change to adjust the rendering process. Initially, most of us get to know shader as a language used to create fancy graphics. I personally dive into shader through the technique known as a toon shader, which transforms game graphics to look like a Japanese animation. But producing this stylish effect is just one of application of shader. The primary function is to control how colors are painted on the screen. The operation of shader can be described as a medieval print shop, well organized with specialized rules. One person might view an original sketch and then draw the outline, and another would color in that outline, and a third would press the design to create the final print. In this process, each person received the work that processed from the previous stage, and then process it before passing it on to the next stage. In essence, each person at each stage has the autonomy to decide how to handle the work that arrives. For instance, the individual responsible for coloring can choose how to apply colors based on the outline they received. This stepwise transformation closely mirrors how shaders function in the random pipeline. Each stage in the pre-shop handles the task independently based on received input. However, in this pre-shop analogy, individuals at each stage do not control how the components of the work they are about to receive are organized, nor can they predict the number of the pieces they will need to process. For example, the person responsible for coloring does not know how the outline will be arranged or how many will arrive. If they receive 100 outlines, then they will need to color all 100, and similarly, pass all 100 finished pieces to the next person. Shaders are part of the overall graphics processing system known as a rendering pipeline. They took the graphical data provided from the previous stage and decide how to alter it before passing it to the next stage. Moreover, shaders execute repeatedly, processing as many units of graphics data as they receive. So rendering can be understood as a pipeline composed of various stages in sequence. In this pipeline, shaders act as a replaceable, swappable middle segments that connect this stage. Let's imagine the rendering pipeline as an entry point where a mixture comes in with each pipe equipped with its own filter. If you replace one of these sections, it will alter the final output that appears on your screen. And shaders are the parts that programmers can directly modify. For instance, consider 3 points that form a triangle entering the pipeline. The way you program your shader can influence whether these points transform into a colorful filled triangle on the screen, or you can also alter the positions of the point of triangle and also choose to draw triangle differently, like only draw outline of the triangle. In this course, we will focus on two main types of shader, vertex shader and fragment shader. A vertex shader is a program that outputs the corresponding screen vertices from the provided 3D vertices. You can think of vertex shader as transforming the position of an object in 3D space to position on 2D screen space, similar to moving an object from real life onto a paper sketch. This process is necessary because even if an object remains the same position in the real world, but the perspective or angle from which you look at it determines its position and size on paper, on sketch. Essentially, the vertex shader decides how the vertices of the real-world object will be spaced on paper. I will explain that in more details later. And then, moving to fragment shader. These work on filling each pixel with color. After the vertex shaders and what's called a rasterizer, which I will discuss later, the fragment shader comes into play. It doesn't determine the position of the object, but define the color to apply to the already defined sketch. Essentially, you are receiving a sketch outline on paper, and the fragment shader works to fill the outline with color, deciding what the final colors of each output pixel should be. There are also other kind of shaders. For instance, compute shader. They are used for parallel processing ability, not for rendering, but for general computing problems. Before we proceed, let's clear up a possible misconception that might arise from comparing shader to the task in the pre-shop. When I explained that vertex shaders move points from 3D space to 2D space, it could be sounds like one worker or one running program gonna move 3 physical points onto a piece of paper all at once. However, this is not how shader operate. Unlike a person who might draw all 3 points at once on a paper, shader leverages the parallel capabilities of GPU. This means if there are number of n inputs, instead of handling all n inputs in a single shader execution, each shader execution handles just one input at a time. But many such executions occur simultaneously. Each vertex of triangle is processed separately and concurrently, resulting in each projected point being output separately. In essence, shaders handle one data point at a time but in parallel, running multiple executions concurrently. Therefore, if there are 100 vertices, each vertex program execution gonna only handle one vertex, but there will be 100 running vertex execution at the same time, and there must be 100 outputs accordingly. In next videos, I will discuss in detail how shaders operate within the render pipeline to shift the triangle from geometry to a color shape on the display. Then see you in the next episode.